MADYN 2000 is a leading rotor dynamics software developed by Delta.js. MADYN 2000 has an integrated rolling element bearing module. In this video, we carry out lateral analysis of a motor with linear and non-linear rolling element bearing characteristics. We open a system with the motor shaft and two shafts for the outer races of the bearings. The latter are needed to apply an axial preload on the bearings. The motor's maximum speed is 12,000 rpm. At station 4 of the motor, we create the left rolling element bearing with speed-dependent properties, 1% damping ratio and axial fixation at the shaft. A deep groove ball bearing with the appropriate dimensions is chosen from the library and the clearance is set. Many additional user settings are possible. Between the motor shaft and the outer bearing races, shaft-in-shaft connections via the rolling element bearings are created. For this purpose, so-called SBS connectors are needed. The outer race of the left bearing, where the preload will be applied, has an axially soft spring to the ground. The outer race of the right bearing is axially fixed with an infinitely stiff spring. For the motor shaft, the lateral and axial degrees of freedom are activated. For the outer races of the bearings, the axial degree of freedom is activated to apply the preload. An axial force of 700 Newton at the outer race of the left bearing causes an opposite reaction force at the right bearing. Due to the coupled degrees of freedom in the bearings, the axial preload causes radial forces on the balls and thus stiffens the bearings. Static analyses for weight load are carried out without and with axial preload. From the deformation plots, it is obvious that the bearings without preload are softer. As can be seen from the linear stiffness matrices of the bearings, the axial preload not only stiffens the bearing, it also makes it almost isotropic. Without preload, the bearing is rather anisotropic. The different bearing stiffnesses without and with axial preload have consequences for the vibration behavior. The natural frequencies of the rotor with axial preload are clearly higher. The influence of the axial preload is also visible in the results of the harmonic unbalance response analysis with mid-rotor unbalance. The peaks of the resonance curves of the radial bearing force correspond exactly to the lateral criticals in the Campbell diagram. With axial preload, the resonance peak is clearly above maximum operating speed. For the vibration analysis with nonlinear bearing characteristics, a transient run-up load case that includes all load components must be created. Weight, axial preload, and unbalance are applied simultaneously. The relation between the relative rotor speed and the run-up time is defined with a function. In the analysis GUI, the initial condition at the start of the transient run-up can be specified. Since the transient response is calculated by means of a bimodal reduction, a Campbell diagram of the free system must exist. The bearings, for which nonlinear properties shall be used, are selected and the bearing damping is entered. A variety of result plots helps the engineer analyzing the sometimes complex vibration behavior with nonlinear bearings. In the orbit plots, it can be seen that the rotor without axial preload does not fully whirl within the bearing clearance. Rather, it moves at the bottom of the bearing because the unbalance force is relatively small compared to the weight load. Other result plots are the vibration amplitude and the bearing force as a function of the rotor speed. In the spectrogram plot, the vibration behavior of the rotor without axial preload generates a complex pattern of speed multiples, whereas only the one-time speed line is visible for the rotor with axial preload. And here is is a final summary of essential features of the rolling element bearing in MADYN 2000. Are you interested in our advanced rotor dynamics software? Feel free to contact us for more information.